So what did I miss? What did I miss?
Hey guys, welcome to this edition of What Did You Miss from Thursday, October 8th for periods 1, 2, and 4, or Friday, October 9th, periods 5 or 7, or welcome if you're just watching the recap. So we started our conversation about forces in class today, and here was our overview slide. So we did spend some time kind of just recapping the assignment that is due for free fall that is due on Monday the 12th. If you have additional questions about that, please see the announcements in my MCPS classroom or check in with me via email. So we took some notes, we did some practice in breakout rooms, and we did some challenges to test out and see Newton's first law in action. So let's go ahead and get started. So the first thing we did is we took, I'm going to actually advance to one that's not done. So as a class, we spent some time like doing a quick activator poll to share 1 to 2 words or phrases that pop into your mind when you see the word forces or Newton's laws. You can still do this if you are not here by accessing the slides in my MCPS classroom, and your words will be added to the Wordle that your classmates have already created, and you'll be able to then see the Wordle recreate in real time to kind of see what you guys already know and what you know in addition to like what your peers said and like what you guys had in common. Because the bigger the word gets, the bolder the word gets, that means more people said it. All right, so we spent some time doing that. We then proceeded to define what a force is. So a force is any push or pull on an object. So anytime you push or pull something, that is considered a force. Now we know that force has an amount, there's an amount of force applied, but it's a vector because it also has a direction. It matters which way we apply a force. If I were to throw this forward towards the screen, that would have a very different direction of motion or result than if I threw it towards myself. So the direction I push something, if I push it to the right, it moves to the right. If I push it to the left, it moves left, up, down. Like that is cause, that motion is the result of the direction of the force. So because the amount of force we apply and the direction in which we apply it matters, force is considered a vector, and when we eventually draw our force diagrams next week, we will represent forces with arrows. So at this point in our lesson, we did head over to Nearpod to access the lesson. You can get to the Nearpod slides in our classroom. They are posted on the same page as the slides are. And we started with Newton's first law of motion. And so let's go ahead and dig in here. So what we started with was a fill in the blank activity. And this was just kind of a quick warm up to see what you guys remembered about Newton's first law. So it might take a couple minutes for the Nearpod to load at times, especially if a lot of people are using it. But this was an opportunity to fill in the blanks, and hopefully you are familiar with Newton's first law of motion. So I'm not going to give away the answers here, but you would then drag and drop from the bottom here the words to fill in some blanks. And so hopefully giving you the first one, an object in motion stays in, like that'll give you a hint on how you should finish this out. So if you are in need of doing the Nearpod, you should definitely go do that because you will get credit for filling this in. When you are done, remember to hit the done button. And since I only put in one answer, it told me like, oh, good try. Like I didn't quite get it. I could try to drag and drop some more, but I think it locks after one attempt. Now, that answer should have been an object in motion stays in motion, an object at rest stays at rest unless acted on by an outside force. That's probably the Newton's first law definition that you got in middle school, and that's fine. Just know that for high school, we are going to get a little bit more specific. And the ways we get a little bit more specific, instead of saying an object at rest stays at rest, we just say that an object will continue in its state of rest. State just means what it's doing. So if it's in a state of rest, that means it's not moving. Now, instead of using the word an object in motion stays in motion, we now are specifying the kind of motion that it has, that it will have a constant velocity in a straight line. That means it cannot speed up, it cannot slow down, and it cannot change direction. It means it's going at one speed in one direction. And that is really important, that objects can either be at rest or move with a constant velocity in a straight line, unless they're acted on by an external unbalanced force. By an unbalanced force, I'm talking about, let's see, the little tennis ball you can see in the video. Right now, this is a balanced force. This tennis ball is at rest. Gravity is pulling it down, but my hand is pushing it up the same amount. And so because those forces are balanced, my tennis ball remains at rest. Now, if I change up how I hold this, if I take away my fingers now, there will be an unbalanced force on this tennis ball. The unbalanced force due to gravity pulling it down, but nothing pushing it back up. It will no longer stay at rest once I let it go because there will be an outside force, the force of gravity, that is unbalanced, and it falls. So Newton's first law says that things will keep doing what they're doing, that it will stay at rest or in motion at a constant velocity in a straight line until a force comes along to change that. All right, so now we did some fill in the blank notes together. So if something is moving at a constant blank in a straight line, it is not accelerating. Remember, acceleration is by definition a change in your speed. So if there's a constant speed, let me drag and drop this, then there would be no acceleration. If there is no acceleration, oh my goodness, which is a change in velocity over time, then that means that there will be no net force. And again, when I say net force, I'm talking about the total amount of force on the object adding up to zero. So going back to the ball example, the net force on a ball at rest is zero because the amount down, pulling down from gravity, and the amount pushing up from my hand, they're equal, they're balanced. And so the net force on the ball is zero. It's not accelerating. And because it's not accelerating, then the forces have to add to zero. It has to be balanced. So anytime you have an object at rest or an object moving at a constant velocity, meaning the speed is not changing and it's not turning, then you have no acceleration and no net force. Now, another name for Newton's first law is the law of inertia. And we have our good old friend here, Bill Nye. And you might remember from the theme song for Bill Nye's episodes that a voice would always say inertia is a property of matter. And basically what inertia is the tendency of an object, so that means the likelihood, how I guess likely is an object to stay at rest or keep moving in a straight line at a constant speed. And that idea, that amount, that tendency or likelihood is what we call inertia. So basically, an object wants to keep doing what it's doing unless there's an outside force to change it. So if something is at rest, it will stay at rest until an external unbalanced force moves it from rest. If something is moving at a constant velocity, unless a force makes it speed up or slow down, it's going to keep moving at the same speed. That's what inertia means. Now we did our final fill in the blanks here with defining how to find inertia. So we use the amount of mass something has, the amount of stuff it's made of, to measure the inertia of an object. So mass is how we're going to assign a value to inertia. Now, the more mass that something has, the more force you would need to give it an acceleration, to change what it's doing. And that means that if you need more force, it would be harder to change its state of motion. And so I want to give you an easy example. It's pretty easy for me to pick up a cell phone. It's pretty light. They're about 750 grams. That's the mass of a cell phone. And mine's on the smaller side, so mine's probably a little lighter. But this is pretty easy. Like, it's not heavy. Like, I'm not getting like a huge workout. But if I were to go and try to pick up a textbook or a backpack, or if I have a younger sibling and I tried to pick them up, they would be bigger than a cell phone. And if they're bigger, if they take up more space, they have more mass, then they have more inertia. And so the larger something is, the more effort it's going to take to move that object or to stop moving that object. If any of you have ever run so fast that you kind of like trip over yourself, that's the same idea, that you are in motion, you have mass. It's going to be harder for you to stop than like a small child who has less mass. It's also why it's easier for you to slow down from like walking. Like if you go from walking to stop, like you can do that almost instantly. But if you're running, you need to like slow down your run and then stop. Because again, you have more mass. Once you're in motion, you want to stay in motion. And since a lot of you are drivers, we did talk about the connection between how heavy a car is, how large a vehicle is, and how easy or hard it is to turn, stop, or accelerate that vehicle. So if you're used to driving a smaller car, if you then drive a bigger one that has more mass, it's going to be harder to brake. So you would need to leave more room to stop because it's going to take more time to slow down because it has more mass. It wants to keep moving. Same idea with if you have a lot of people in your car or a lot of stuff in your car and you don't normally have that much stuff, having more mass in the car is going to make it harder to stop that car while you're driving. And the same idea, like it's going to make it harder to take a turn. And so you just kind of have to get used to the type and size car that you have to kind of know like how much to turn the wheel or how much to press the pedals. But just know that by adding more people to a car or truck or more stuff to it, that it changes the amount of inertia that it has, and that will affect the outcome of how you drive. So that is a real life application right there. And then we looked at these two pictures because they sum up that idea that an object in motion stays in motion. Seatbelts are crucial because the tires here stopped the motorbike, but they did not apply an external force to the person on the bike. So the person on the bike is an object in motion, and they stayed in motion because the tires did not touch them. There was no outside force. The same idea happened with this giant truck carrying this big hunk of marble. This was a real truck that this happened to. So the brakes stopped the truck, but there was no outside force. There were no brakes on the big marble slab in the back, and it just kept moving forward into the front of the cabin of the truck and just burst right through the trailer. So an object in motion will stay in motion. An object at rest will stay at rest unless acted on by an outside force. And the amount of mass something has will dictate how easy or hard it is to change the motion of an object, whether it's at rest or moving. For the rest of today's notes, we did look at 2 more slides and did some hands-on practice. So for the second half of what you missed in this class, for part 2 of What Did I Miss, tune in to the second video, please. The last concept we talked about today relating unbalanced and balanced forces was the idea that balanced forces should be equal in size and unbalanced forces are not. So if we look at this image here, we can see that the arrow that's pointing to the right is larger than this arrow pointing to the left. That would mean that the force pushing to the right is larger than the force to the left, and the object would end up moving to the right in the direction of the larger force. And so knowing if forces are balanced or unbalanced will help us make predictions about how something will move. But if something is following Newton's first law, then the forces should be balanced, and we can say that that object is in a state of equilibrium. Now, equilibrium looks a whole lot like the word equal, and it's a similar meaning. Like the forces should be the same in each direction, meaning that whatever is your total amount of forces pointing up will equal your total amount of forces pointing down. So in the case of this first diagram on the left here, we have 50 newtons pointing up, 50 newtons pointing down. If I were to find the net or sum of these forces, I would have positive 50 up plus negative 50 down, because we make the down and left directions negative in physics, because the negative sign tells us which way we're going. So we'd have 50 plus negative 50, and that ends up being 0. So that means that this block is not going to move up, and it's not going to move down at a changing rate. It could be moving at a constant speed, but it can't speed up or slow down. And if it's at rest, it would stay at rest. Looking at our horizontal forces, those are also balanced, which is why this whole object is in equilibrium. The amount of force to the right is 30 newtons, so positive 30. The amount to the left is negative 30. 30 equals 30. My left forces equal the right forces, and my net force is 0, because 30 plus negative 30 to the left is equal to 0 newtons total. In both of these pictures, though, you can see that the vertical forces are different from the horizontal ones, and it's still in equilibrium. So equilibrium doesn't mean that every force acting on the object is the same. It just means that the total force happening vertically up and down is 0, and that the net force happening left and right is also 0. So that is the idea of equilibrium. And anything that follows Newton's first law is in equilibrium. We then spent some time doing some first law challenges. If you want to try them at home, I think it would be great. I do want to caution you against the tablecloth pull. If you're going to try that at home, make sure you get permission first and that you use things that cannot break. So plastic plates, metal silverware, plastic cups. Like, do not try this with really nice dishes, plates, or glasses, because if something goes wrong, they can break. And so I just want to put that warning out there and that disclaimer out there that I'm not telling you to try this if you don't need to, or if you don't have access to like plastic dishware, because things can go wrong. Seeing the demo is enough to prove that Newton's first law works. So I'm going to take you through a couple demos now, and you can try them on your own, or you can just observe and know that physics works. All right, for this first challenge, you're going to need a coin or some other small object. So if you don't have access to a coin, something small like an eraser could work, or a pencil or a pen. As long as you can balance it on the back of your hand, then it's small enough to try. Now, Newton's first law says an object at rest should stay at rest unless acted on by an outside force. Well, right now, there's no net force on this coin. Gravity pulls down, my hand pushes up. The coin is at rest. If I take away my hand, then the coin will experience the net force due to gravity and will start to fall. If I pull back my hand quickly, I might be able to catch that coin before it's able to free fall too far to the ground. So that is challenge number 1. Sometimes I get it, sometimes I don't, so we'll see. So, haha. So you can catch the coin. It is cheating if you pop the coin up into the air. You're supposed to pull your hand straight back and grab the coin. It helps if you have your hand open so that you can just close it around the coin real quick. So that is challenge number 1. The second challenge, I can't do it. My shoulder, I've dislocated it before. I can't rotate it fast enough. But basically you would put your elbow so it's parallel to the floor. You then balance the coin or small object on your elbow, and then you would try to catch it on the way down. And so I didn't catch it. But sometimes you're able to, because again, when your elbow rotates out from under it, the coin would then start to fall, and you can catch it before it falls too far. So those are 2 quick challenges you can do with just the coin or small object. The next one is going to involve using a jar and a coin and a piece of paper or index card. It needs to be like a playing card or an index card. Like a flimsy piece of paper is not going to be sturdy enough. So let me set that one up and we'll do that demo next. I do have this set up so that there's a little background behind it to make it a little easier to see the jar. So I'm going to take the playing card or index card in this case, and I'm going to place it on top of the jar. And then I'm going to place a coin on top of the index card. And what this is going to do, I will apply an outside force, an external unbalanced force to the index card, but I'm not going to apply it to the coin. So right now the coin is in equilibrium. The pull down from gravity is equal to the push up from the card. If I knock the card out of the way, there's no balanced force to keep gravity from pulling the coin into the jar. So if I hit this just right, if it's perfectly horizontal, then the coin will just fall into the jar. Now if I hit upward in any way, like the coin will flip off the top. So if you're going to try this, you need to flick the card really quick and it should work. So let's give it a shot. And there you have it. Fell right into the jar. Because it was an object at rest that stayed at rest until it was acted on by an external unbalanced force, in this case the force due to gravity. Our next demo is going to focus on inertia. I'm sure you guys are familiar with textbooks. They're pretty sturdy, pretty heavy, a lot of mass, and so they have a lot of inertia. The more mass something has, the more inertia it's got. So if I drop this, even though that was a short distance, like it's not going to fall very far, but the force it would take to stop that book once it's in motion is going to be fairly large because it has a lot of mass. Now, that probably would like break a finger or a toe if you were to drop like a book of this mass onto like your hand or your foot. But what's interesting is that if you place it on your hand, it's now an object at rest. And because it has a lot of mass, it wants to stay at rest. So if I drop something on it, like let's say this stapler, if I drop this onto the book, you would think it would hurt my hand. But believe it or not, the book wants to stay at rest. And so I might feel a little pressure, but it's not going to hurt my hand. And that is going to be inertia at work. So again, it sounds like a loud crash, but I really didn't feel it on my hand at all because again, this book has a lot of mass and so it wanted to stay at rest, so the force hitting it from the stapler falling wasn't enough to really get the book moving. Now if you drop something heavy enough onto something on your hand, yes, it will hurt, but small objects like this right here, like I feel it in my hand, but it doesn't hurt. It just feels like pressure. So that is an example of inertia in action. And then last but not least, we have the tablecloth pull. Now, I do not have a literal tablecloth, so I had to improvise a little bit. So I have a giant piece of poster paper. Again, my disclaimer is plastic everything. This cup, plastic. This plate, plastic. Silverware, metal. So like none of this is breakable. I am in no way advocating that you should try this with anything that is. It is going to be more challenging the larger the table or the tablecloth is. I did try it with a pillowcase earlier because I don't have a tablecloth, and the pillowcase, because it's double layered, it created friction and caused things to fall. So theoretically, if I pull on the cloth, my tablecloth in this case, my piece of poster paper, everything should stay where it is. So let's go ahead and give it a try. So, oh, usually I let you guys do this. Oh, so I didn't pull fast enough. So there was a little bit of friction. Let's try it one more time. Just reset real quick. Take two. So ready? There we go. So it didn't go anywhere because the external force was applied to the paper. It was not touching this. And so because of that, it's just like the coin falling into the jar. The force wasn't applied to any of the items you see here, so they didn't go anywhere. And so those are some examples of Newton's first law that we looked at all together in class today. We just have one final slide to look at, and then this session of What Did I Miss is done. The final part of class today was spent practicing applying Newton's first law in breakout rooms. So to do that, we went to modules. We went to our current week, which is week 6, and we found the Newton's first law discussion questions. And let's go through the instructions together. We actually leave student view so that I can open it. Now, this is what I call a 3-color assignment. You are going to use 3 different colors of font to complete your assignment. The first color you choose is for any work that you did just by yourself, just you, your brain, and your notes. So that would be the first color. Anything you wrote down after discussing the question with your breakout room would be the second color, because that was done as a team. When we go over this as a class on Monday, you will then type any additional notes for yourself when we review as a class in a third color. Now, some questions might only have color number 2 and color number 3 if you start brainstorming with your team now, and then we go over it on Monday. If your answer matches the team's answer and matches the class answer, you can just indicate that when we review to show that you are checking your work. If you can stick to the color codes here so that anything that you type yourself, or it's just you, your brain, and your paper, is in red, anything you work on after talking as a team is in blue, and then anything we go over in class is green, that would be great. If you decide that you want a different color scheme, that is fine, but if you could just change it at the top here so I know which color you are using for which type of thinking. And this is important. As you work, there should be no deleting or backspacing. Like, if you had it and you change your mind after talking with your group, that's fine. That's what the different color is for. It's to show how your thinking changed as our discussion group got bigger and bigger and bigger. So this is not only a good study tool for when we go to review Newton's first law when we eventually have a quiz on forces, but it kind of lets you know what you could do by yourself, what you could do with a team, and what you could do as a class member. So it'll kind of give you an idea of how much studying or practice you need with a topic, and if you need to ask me for help. It's fine if you do. But I do expect to see at least 2 colors, if not 3, for every question. Now, we had about 15 to 20 minutes depending on the class period, and so my expectation was that as a team, you would discuss questions 1, 2, and 3 by the end of class on your class period day. You will then, over the weekend, make sure you jot down your thoughts for questions 4, 5, and 6 so that you are ready to discuss them in your breakout room on Monday or Tuesday next week. We will then discuss them in the class, and your group will randomly be picked to present one of the 6 questions. There are 6 breakout rooms in each class, and so we'll randomly call on one of the groups for question 1, a different group for question 2. So there's no way to know ahead of time which question you'll be asked to present. And I am asking that you include at least 1 relevant fact from the forces fact sheet, which is linked here. in your reasoning for like how you determined your answer to each question. So that is an overview of what we did in class today. Some other reminders from our last slide are going to be shown. So again, before our next live class, you should have attempted all the questions. You do not turn it in to my MCPS classroom until after we've gone over it in class on Monday. That's when you'll submit. So do not submit until after we finish reviewing the 6 first law discussion questions in class on Monday or Tuesday. If you have not posted your 4 free fall Flipgrid videos yet, you should have that done by Monday at 10 p.m. That provides you with some time to ask for help, and I do have live office hours on Monday from 2:45 to 3:15 p.m. where I can field last-minute questions. If you owe me work from September, weeks 1 through 4, the last day I'm going to take any late or missing work from September is Wednesday, October 14th at 10 p.m. Again, this will give you a chance to ask for help. There's Wednesday check-ins. If you have any last-minute questions on Wednesday about what you're missing or what has or has not been submitted, but if it's from the first 4 weeks of school, I should have it by that date. Finally, if you are retaking the quiz, the expectation is that you will have retaken it by Sunday. The code is posted in the announcement in my MCPS classroom, which you can get to at either the top of your screen or using the announcements quick link at the bottom of our page. So, that being said, I will see you guys on either Monday or Tuesday, and I hope you guys have a great weekend.